The function f of x equals x squared satisfies the property that when the input is changed to minus x, then the output remains unchanged, because minus x squared is equal to minus 1 squared times x squared, and the minus 1's multiply together to produce 1. In other words, this function satisfies the property that f of minus x equals f of x for any x in its domain. In contrast, the function g of x equals x to the third satisfies the property that when the input is changed to minus x, then the output changes by a minus sign too. This is because minus x to the third is equal to minus 1 to the third times x to the third, and the minus 1's in this case multiply together to form a minus sign. The property that g satisfies can therefore be summarized as g of minus x equals minus g of x for any x in its domain. We realize that this minus sign was obtained in the case of g because there was an odd number of minus 1's, which came from the odd power of 3 in the exponent. In fact, whenever the exponent, say n, is odd, then the power function h of x equals x to the n changes by a minus sign when the output is changed by 1 too. That is, when n is odd, then the function h of x equals x to the n satisfies the property that h of minus x equals minus h of x. On the other hand, when the power of n is even, then the output remains the same even when the input is changed by a minus sign, because the minus signs will pair together in an even way upon expanding in the multiplication. These two different types of behaviors have names, and they're actually named after the two different types of parities in the exponents of these functions. In other words, any function k of x is called an even function if k of x satisfies the property that k of minus x equals k of x for each x. On the other hand, if the function k of x satisfies k of minus x equals minus k of x, then it's called odd. For example, the function cosine of x, which satisfies cosine of minus x equals cosine of x, is an even function, whereas the function sine of x is an odd function because it satisfies sine of minus x equals minus sine of x. These symmetry properties are also reflected in the graphs of these types of functions. For example, the graph of f of x equals x squared, which is an even function, enjoys a symmetry across the y-axis. This is because the condition of being even is that f of minus x equals f of x, meaning that the inputs of minus x and x must produce the same output. What this means for the graph is that the inputs of minus x and x must rise to the same vertical output along the graph, which means the corresponding points on the graph must lie on the same horizontal line, and must therefore be mirrored across the y-axis. On the other hand, the graph of g of x equals x to the third, which is odd, enjoys a different type of symmetry. In this case, the symmetry is around the origin, in the sense that the graph remains the same when rotated a half turn around the origin. This rotational symmetry can be understood as a symmetry that arises actually in two steps. First, by reflecting across the x-axis, and then across the y-axis. Algebraically, these two reflections are expressed by the two minus signs that occur in the symmetry property for an odd function. The reflection in the horizontal direction is indicated by the minus sign on the input, and the reflection in the vertical direction by the minus sign next to the output. Using this geometric understanding of symmetry, it's easy to see that the absolute value function, whose graph is this v-shape, must be even because it enjoys the symmetry across the y-axis characteristic of even functions. Parity is subject to certain multiplication rules, which are analogous to the way in which powers of minus 1 behave. For example, the product of two even functions is even, whereas the product of two odd functions is even as well, roughly because the product of two minus 1's is a 1. These multiplication rules can also be verified directly with the necessary algebra. For example, if f is even and g is odd, then this means that we have the relations f of minus x equals f of x and g of minus x equals minus g of x. If we set h of x to be the product of f and g, meaning that h of x equals f of x times g of x, and investigate h of minus x, we see that it's equal to f of minus x times g of minus x, which, using the even and odd properties of f and g, becomes f of x times minus g of x. Pulling the minus sign out in front, we see that this is equal to minus h of x itself. What we have obtained, therefore, is that the product of an even function with an odd function is odd. The property of being even or odd extends more generally to any relationship between the variables x and y. For example, the unit circle is described by the relationship x squared plus y squared equals 1. And even though this doesn't define y as a function of x, it still describes a relationship between the variables. This relationship between the variables x and y is even in x because upon replacing x by minus x, the equality remains the same. Geometrically, what this means is that the equation describes a set in the plane which is symmetric across the y-axis, that is, symmetric upon the transformation that sends x to minus x. From this geometric viewpoint, it's also clear that this curve enjoys rotational symmetry about the origin too, characteristic of odd functions, and so this should be reflected algebraically in the equation as well. For this type of odd symmetry, the relevant algebraic property satisfied by the equation is that upon replacing both x and y by minus x and minus y respectively, the equality remains the same. For the unit circle, this is clearly the case because both x and y appear in the relationship with even powers associated to them.